This lecture introduces Euler's formula and how to find the real solutions for complex exponentials when we have a complex root of the characteristic polynomial in second-order homogeneous differential equations with constant coefficients. So let's talk about Euler's formula. Euler formulas give you an idea on how to express when you have an exponential, when you have a complex exponential, e to the I theta, where theta is a value in R and z is a complex value, z equals to alpha plus I beta. And z is a value in a complex field. So then one can use Euler's formula to write the complex exponential e to the I theta equals to cosine of theta plus I times sine of theta. So remember, if we have e to the zt, z of t, and z is alpha plus I beta t, then we can express this exponential in terms of sine, cosine, and also in terms of exponential functions, e to the alpha t cosine beta plus I times e to the alpha t sine of beta. And this is the complex part, and this is the real part. All right. So noting that if z bar is a conjugate of z, then e to the z is also the conjugate of e to the bar of z bar of t. Okay. Well, remember that if we have that this is the root of the characteristic polynomial, then we have a function's solutions y1 equals to e to the zt, right? And zt is alpha plus or minus I beta t. And then we're going to have this. So we have a1 is, it's going to be e to the alpha t cosine of beta plus I e to the alpha t sine of beta t. So this is E1. And then E2 is Y2. The second solution will be e to the alpha t cosine of beta t minus I e to the alpha t sine of beta t. Okay. Well, as we know that if these two are the solution to a differential equation, then the linear combination is also the solution. So if I take y1 plus y2 divided by 2, I will have, I will cancel this term, and then I will have e to the alpha t cosine beta of t. Okay, and if I take y1 minus y2 over 2, then I will have e to the alpha t sine of beta t. So as you can see that this is also a, let's say x1 is also a solution to the differential equation, and also x2 is a solution to the same differential equations. So we have two real roots here, e to the alpha t cosine of beta and e to the alpha t sine of beta. And both x1 and x2 are solutions to the same differential equations. You see that this is how we're extracting the real part of the solutions to find the real solutions for the differential equations. All right, so let's summarize what we just did. If R, right, the root of the characteristic polynomial is a real root, is a complex root, if R equals to alpha plus or minus I times beta, is a characteristic root of the second order linear equations with constant coefficients, then the real solution, general solutions is given by complex exponentials. These solutions right here can be written as y equals to c1 times e to the alpha t cosine beta t plus c2 e to the alpha t times sine of beta t. Okay. So keep in mind, if you have a complex root, then you want to think of cosine and sine involving beta and then e to the alpha t. Again, alpha and beta here are the real part, and I here is the complex part. So let's look at an example. You want to find a unique, particular solution to each of this initial value problem by first finding the general solutions. So I have a second differential equation, second order, with all constant coefficients. I know that the first thing I want to do is I want to find the general solutions, but the first thing before it is I want to find the characteristic polynomial. So I found the characteristic polynomial is r squared plus 25 equals to 0. So that would means r equals to plus and minus negative of 25, right? And I know that I have to use a complex value in order to express the square root of negative 25. So it's going to be plus minus I 5 or 5i. All right, so in this case, I have a complex root. My alpha is 0 and my beta is 5. So this is beta and this is alpha. So alpha is 0 and beta is 5, keep it in mind. So then I can use this formula here to come up with a general solution. So the general solutions is y t equals to c1 e to the alpha t, where alpha is 0, so it's just going to be 1, cosine beta t plus c2 e to the alpha t, and again alpha is 0, so it's just going to c2 sine of beta t. Okay, so I found my general solution. So the next things I need to do is I have to find the particular solution using these two initial values here. So I have the first initial value, y0 equals to 1, and the second initial value involved y prime. So that means I want to find y prime before I plug the initial values into these two functions, right? So from here, you can have y prime equals to c1 beta negative sine of beta t, okay, plus c2 beta cosine of beta t. All right, now as you can see that I can plug 0, 1 into y of t, and I can plug 0, 1 into y prime of t. Okay, so if I plug 0 and 1 into here, plug in 0, 1, so that means t equals to 0, t equal to 0. So I have 1 equals to c1, cosine of 0 is 1, and sine of 0 should be 0. So c1 equals to 1. And I plug y prime into here, I have 1 equals to sine of 0 should be 0, c2 beta cosine of 0 is 1. So I have c2 equals to beta. One thing that I forgot to do is I should replace beta by 5. Okay. So then that means c2 equals to 1 over 5 because beta equals to 5. So I found C1, I found C2. I can plug these two informations and this general solutions together to find my particular solution. So particular solutions. It's going to be y of t equals to C1, which is 1, cosine of beta t, which is 5t, plus C2 is 1 over 5 times sine of 5t. So this is my particular solution. And this is my general solutions. All right, let's go to the next example here. So again, I have a second order differential equation with constant coefficients. So my goal is I want to find the characteristic polynomial, which is going to be r squared plus 4r plus 5 equals to 0. Okay, and then I will try to solve this equation. So I have -4 plus and minus 4 squared minus 4 times 5 times 1 over 2. So I would have -4 plus and minus 16 minus 20 is -4. So I know that I have a complex root because I have a negative value inside the square root. So I'm going to go ahead and simplify this. It's going to give you me -2 plus and minus is going to be 2i. So at this point, I can identify, so this is my alpha and this is my beta. Okay, so then I know that I can use a formula to find the general solutions y of t equals to c1 e to the -2t, which is alpha, cosine of beta, which is 2t. Cosine of 2t plus c2 e to the -2t and multiply to sine of 2t. Okay. So this is my general solutions, y. And then again, because I want to find the particular solutions involving two initial values, I need to find y prime of t. It's going to be C1, you have to use a product rule here. C1, the derivative of the first one will be -2 e to the -2t cosine of 2t. And then plus C1 e to the -2t multiply to 2 and negative sine of 2t. Okay, so that's t prime. For the first, this is the derivative of the first functions. And then I have to keep going to find the derivative of the second functions here. So I would have plus C2 -2 e to the -2t times sine of 2t plus C2 e to the -2t times 2 cosine of 2t. Okay, so this is the first derivative of y and y prime. Now I need to plug the initial value into these two functions to find C1 and C2. So using 0, 1 here, I plug 0 into t and 1 into y. So I have 1 here equals to 0. So this is going to be just 0. The whole thing will be 0. And I just have this, right? So it's going to be C1 e to the -2t and t is 0. So it's just e to the 0, which is 1. So C1 times cosine of 0, which is just C1 equals to 1. So this is using initial value, right? Using the initial value on the first derivative functions here, again, I have 0 and -1. So I would have -1 on this side equals to, so if I plug 0 into sine, I would have, this is going to be 0, this is going to be 0. I only have two functions left. So it's going to be C1, -2, right? -2 C1. negative 2c1 e to the 0, which is 1, cosine of 2t, which is 1. And then the second term, I would have 2, right, c2 e to the 0, which is 1, and cosine of 0, which is 1. So that means I would have negative 2c1 plus 2c2 equals to negative 1. And I know that c1 equals to 1. So that means c2 gonna be equals to, if I plug 1 into here, right? I would have negative 2 times 1 is negative 2, and move it to other side, so it's going positive 2, negative 1 plus 2 will be 1 divided by 2, so 1 over 2. So I just found that C2 equals 1 over 2. So then I can use C1, C2, and the general functions in order to find my particular solutions. Particular solution would be y of t equals to c1, which is 1, so e to the negative 2t cosine of 2t, plus c2 is 1/2 e to the negative 2t times sine of 2t. Here we go. I just found the particular solutions for this IVP. Using the general solutions, getting from the complex root of the characteristic polynomial, and also I was using the two initial values here in order to find C1 and C2. And once I have C1, C2, and general solutions, I could have the particular solutions in this form. Here we go. Just introduce how to find the real solutions for complex exponentials when you have a complex root for the characteristic polynomials of a second order linear differential equation with constant coefficients.